How's it going, everyone? So in this video, we're going to look at a little more about content from section 3.3, which is about static equilibrium analysis in 2 dimensions. Remember that the tool that's utilized in order to do that analysis is known as a free body diagram, which I'm abbreviating here by the acronym FBD. In addition, your book uses a term coplanar force systems, which really just describes scenarios in which all of the forces acting upon a body live in a 2-dimensional plane. So that's just a fancy way to say that this is a 2D problem. So before, I kind of wanted to do another example that gave us a little bit of a kind of engineering motivation, a little bit of a feel of why. So it's not the best example, of course, because I have to use a diagram that's from a problem in the text. But imagine that you have this barrel and you know the mass of the barrel, so you know its weight, and you basically have to keep it suspended from the ground. But for some reason, you just actually can't attach a cable to the top of it directly to the ceiling. You're just restricted from a geometrical point of view. Instead, your points of connection are some point on the wall to the left and some point on the ceiling, but not directly above. And because of that, you have to kind of use this complex scenario in which the cable that's actually bearing the weight of the barrel is attached at an adjoining fastener to a cable that runs 2 point D in the horizontal direction and a cable that runs 2 point B in the upper right direction. So say that someone just did this and they say, hey, I don't know if this thing is going to work, right? That cable that we use, it has a maximum tensile strength. There's a maximum kind of internal force that it can withstand. And as we'll see a little bit later on in the course, that internal force is actually related to the external forces that it can exert on objects. So the question being, if you knew the mass of this barrel, could you actually calculate what the load or the internal forces are, in this case, in the cable? So just forget that I said internal forces until we get much later on in the course, because we're really not trying to think about those for now. But what we want to do is just see if we can find the amount of tension that each of those cables is exerting on the various bodies within our scenario here. So as an engineer, you want to get the right answer, but you also want to get it as quickly and as cheaply as possible. So maybe you could run like a finite element analysis, very complicated computer program in order to solve this. However, we're just going to use the back of the envelope type static analysis and just see if we can get our answer in a more simplistic way. And what we're going to find is that in this scenario, we're actually going to be able to get it in an incredibly simplistic way, because we're going to be able to deploy a particle model, which means that we can ignore the underlying geometry of the actual problem setup. So let's see how that would actually work. So remember that when you're trying to do a free body diagram, you're trying to segment some portion of the body that allows you to isolate the various forces of interest. So if the forces of interest are the actual tensions in those cables, we want to segment some portion of this body that would involve all of the tensions in the cables, or the forces that are exerted by the cables on something. So if you just look what's going on here, like if you were to draw a free body diagram of the barrel itself, right? And let's just kind of go to the dot cam and show you what I mean by this. So if I just draw a free body diagram of the barrel itself, remember that what that means is I'm going to separate the body, in this case the barrel, from all of its surroundings. And I'm going to draw all of the forces that act upon that barrel on that free body diagram. So there would be the weight of the barrel, which is just going to be its mass times the constant acceleration due to gravity. Since we're modeling all of these problems, the gravitational force is modeled as constant near the surface of the Earth. In addition, that gravitational weight kind of pulls the barrel towards the Earth, but the cable which is attached, and I'll kind of go back to the original drawing here, is going to pull that barrel up at the point of connection of that little hook on the top. And if you notice both of these, so I will usually, the way that your text will label forces that are exerted on bodies by cables as ST, which is a tension, but that kind of gets into understanding the idea of an internal force. So I'm just going to label this as TA. But if you notice the line of action of those two forces, even though they're distributed across the body, we usually model the weight as acting at the center of gravity. We haven't described what that is yet. But if you have a kind of symmetrical weight distribution, it will always occur at the point of intersection of lines of symmetry. So assuming it's a normal cylindrical barrel, that's going to be right at the middle. And again, of course, this barrel lives in 3 dimensions, but we're modeling it in 2 dimensions. In addition, although this actual force that's applied, kind of yanking the barrel up by the cable, portion of the cable that is connected between A and C, so kind of this vertical cable here, even though it's applied at this point, notice that its line of action also passes through the center of gravity of this barrel. So what that means is I can actually use a particle model, and the reason that I can use a particle model is because those two forces are called concurrent. So if I were to employ a particle model, I can just represent that barrel, which has finite dimensions, as a dot. On that particle, I have the weight acting in the minus y direction, or the minus j hat direction, and I have the tension exerted by, I should say the force exerted by that cable, which we're denoting as a tension, counterbalancing that and pulling up, assuming that the actual barrel is not moving. But what's the problem with kind of analyzing the barrel as a free body? Well, the problem is this allows you to find the tension in rope A, but no tension in rope B or C. So the question is there another body, and I should say B or D, of course. The book has to be weird and just, C is for some reason the actual barrel in this case, I see. So the question is there a body in this diagram that we could kind of segment and cut out of its surroundings and have in our free body diagram representation of the three unknown forces? And of course, there is a particular part of the body that we could segment, and it's this little adjoining kind of circular hook in the middle. Notice if I analyze the circular hook in the middle, if I were to remove it from its surroundings, it is pulled down by this portion of the cable going from A to C. So that's our TA that we talked about. And just so we don't need to get to this level of complexity right now, but if you think about it, what really is going on, I'm going to draw the entire bottom of the physical situation. So this is my barrel, this is my cable, and then that's my little hook. So we know if everything's in equilibrium, well, naturally the weight of the barrel is always going in the downward direction. So what that means is that the cable must actually pull the barrel in the upward direction. However, remember that Newton's third law says that for each force that's exerted on an object, you have the equal and opposite reaction pairs. So what that means is as the cable pulls the barrel up, the barrel pulls the cable down. And in addition, since this cable must be in equilibrium as well, or another way to look at it is, if the cable is exerting a downward force on the circular hook, then the circular hook is exerting an upward force on the cable. So if you notice all of these, you can call them all TA, but in order for this thing to be in equilibrium, they're all equal to W. So what you actually find here is that this portion of the actual cable is kind of bearing the weight of the underlying the barrel. So the beautiful thing about actually isolating the circular portion of the hook is just like the cable, the portion of the cable A pulls it down, this portion of the cable, which is B, pulls it up to the right, and this portion pulls it over to the left. So we can actually do some analysis here and actually see what these turn out to be. But let me just kind of show you that. The point I was trying to make is that's why you actually segment the hook here as the body of interest within your free body diagram, because freeing it allows you to draw a diagram that involves each of the forces of interest. And that's all that this is saying in this scenario. And do remember, when we actually draw a free body diagram, we're going to try to put as much physics as we can into the diagram to make it easy to solve. Really what we're trying to do there is to reduce the number of unknowns such that we have what's known as a statically determinate system. We'll see that here in a minute. So the nice thing about this particular scenario is, since all of the forces that are exerted on that circular hook by the cables are kind of cable-related forces, we talked about how in the earlier lecture this week, those are always going to have a direction that's aligned along the cable itself. So even though forces, generally speaking, will have an unknown magnitude and direction, these three forces, we actually know the directions. And as I mentioned a little bit earlier, we actually know the magnitude of this force as well. So what does it mean to actually apply equilibrium conditions? So the ideal being that if I have a free body diagram that is actually exerted, in this case, on the circular hook, and if you notice the reason that the text is saying that you know the magnitude of this force is related to what I was showing you on the dot cam, this has to be equivalent to the weight of the barrel. So when you apply equilibrium conditions, you're basically saying, if you're working with a particle, that the sum of all forces in the horizontal direction must be equal to zero. And in addition, the sum of all forces in the vertical direction must be equal to zero. If you think about that from kind of a linear algebra point of view, what that means is that, generally speaking, you'll have two linearly independent equations, which will allow you to solve for two unknowns. And fortunately, even though when we first drew that free body diagram, it kind of looked like there might be three unknowns that we might have, namely the magnitude of each of those tensions, what we see kind of based upon our physical intuition and the analysis that we did is that really that tension in the vertical bottom portion of the rope is known, it's just the weight. So this is a scenario in which we can enforce two conditions of equilibrium. Sum of all forces in the x direction must be zero. What that means practically is that the pull of this cable to the left must equal the component of the pull of this cable to the right, and sum of all forces in the vertical direction equals 0, which just means that the vertical component of FB must counterbalance the weight of the barrel in this case. So we are going to be able to solve this. So what that means is that we have a statically determinate system. So the question, and kind of at a 200 level course, given the level of mathematics that we have, we're not going to talk about how to solve a pair of linear simultaneous equations. However, if I actually do any of them by hand, and I think due to the time crunch this week, I might give you an actual older video for an example problem that I did a little bit later. And I believe in that I actually set the problem up from a linear algebra point of view and show you again how to use MATLAB like I did for one of the chapter 2 problems in case you're interested. So hopefully that makes sense to you. Again, the key point being that if we're asked to solve for particular forces in reaction, such as in a cable, we need to find a portion of our actual physical situation that we can segment and draw a free body diagram. Ideally, on that portion of the free body diagram, all the forces of interest will act. And in the two-dimensional scenario, since we have two equations of equilibrium, we're able to solve for two unknowns. If we were to have more than that, it doesn't necessarily mean that the body is not stable. Like you can kind of think to yourself, what if if someone put a redundant cable that you didn't need going up? Clearly, that could still support the weight. It would still be stable. However, in that case, we would have a statically indeterminate situation because there would be more unknowns that we can solve for given the amount of actual linear independent equations we can write, which in 2 dimensions for particle is 2.